All right. The next thing we're going to look at is forming images from a spherical mirror. And again, remember we said that if we have a point source of light, that light comes out in all directions equally from it. And what we'll look at then is where the light looks like it's coming from when it's reflected off of a spherical mirror. So in the diagram we have the center line that was going through. Then I have a point of light, and it's up the tip of my finger here. So the light from up here is going again in all directions outward from it. And it turns out the spherical mirror does end up producing what's called a focus. And so the light rays do end up appearing to come from a particular direction. The proof of that is not fun either, but it is a fact. Most other types of shapes of mirrors will not do that. So it's a spherical mirror will be one where the light does appear from wherever it comes from. It will appear to come from a particular location. So given that will be a fact, if we have light then that's coming from a particular source, we have a mirror over here, then the easiest way to be able to find where the group of light comes from is to end up, again, light comes in all directions here. There are two directions that are particularly easy to be able to predict. One of them is the one that ends up going down to the center line. So at the center line, the mirror, even though the mirror is curved, that the tangent to it at the midline is flat. And so it will end up reflecting off the normal here, and will reflect off exactly with Archimedes' principle. The angle of incidence will equal the angle of reflection. So you can end up drawing that particular ray trace very easily that way. The other one is the one that would be coming in horizontal. And in order to know where that goes, remember what we said just before with a focus, that the light that would go there will go into the focal point. So the focal point, if it's convex, is behind the mirror, so you'd end up doing that. If it's concave, it'd be in front of the mirror, so you draw the light ray coming this way. So if those two light rays intersect on one side of it, then the location where those two intersect will also be the direction that all of the other possible light rays you could draw would also intersect there. But again, those were the easiest ones to geometrically draw. And that will end up being the location then of the image that you'd end up having. In the case of a convex lens where it's behind the mirror, then your light ray will come in this way, and then you draw it like it's going to go back behind the mirror. Now, of course, the one that would come in this way will bounce off like that. So in order to find where the image of it is, you'll end up, the light ray comes out this way, but then it would look like it would come from back up here. So you would end up drawing it back this way until that ends up intersecting with the ray that ends up going to the focal point behind the mirror, and then that would end up describing where the location is of your image. The spherical mirror equation is not too difficult to write down. Again, the proof is ugly. You can end up looking in your text and they end up showing you where it comes from, but again, it's just not very pretty to prove. We'll end up writing notationally, and I think your text only uses O and I instead of DO and DI. The reason I don't write an O is because it looks like a zero. So D sub O is my object distance, D sub I is my image distance, where I think your text just uses O and I. And what those represent, the object is where the light comes from. So that's the physical source of the light. We'll talk about where it can be something slightly different in thin lenses next session. But for a mirror, it is the literal location of the object relative to the center line midpoint of the mirror. So it's how far it is away from the mirror. That's going to be your object distance, and it's always positive because your object always has to be where an object is. It has to be in front of the mirror for you to get a reflection. So the reciprocal of the object distance plus the reciprocal of the image distance is the reciprocal of the focal length. Your image distance can be positive or negative. A positive image will end up being where the image is on the physical side of the mirror, where it's on the same side as the object is. A negative image distance is where the image appears to be behind the mirror, which again is something that you're already familiar with the idea of looking at a flat mirror. So that's what those two that's how those are defined, and the positive direction for both the object and the image distance is in front of the mirror. We'll also see with thin lenses that's going to be a little different. So because what we'll see is the two equations we're going to introduce in this one will be exactly the same equations that we'll see for thin lenses, except the difference is for thin lenses, the object distance and image distance are not on the same side of the thin lens. The object and image distance for a spherical mirror are both in front of the mirror. The positive focal length is in front of the mirror. All right, so then I end up going through and solving that for my image distance. And in terms of understanding what that will mean, that if my focal length is negative, then the absolute value of that will drop the minus sign with the focal length. Then DO minus F will be more than F. So the denominator is bigger than F. So if I take F DO divided by that, it will be less than DO. So if your focal length is negative, your image distance is always smaller than the focal length. So it's always is always smaller, than the object distance. So it's always closer to the mirror than the object is. And we'll end up talking about why that makes a difference in the next one, where we introduce what magnification is.